How does the interrupt vector table direct program execution? Imagine you're playing a game where different buttons trigger different actions. When you press a button, the game instantly knows where to go to perform that action. In microcontrollers and embedded systems, something similar happens with interrupts and the interrupt vector table. The interrupt vector table is like a map stored in a fixed spot in memory. It holds the addresses of special functions called interrupt service routines. These routines handle specific events like a button press or sensor signal. When an interrupt occurs, the processor needs to jump to the right routine quickly. First, the processor detects an interrupt signal from a device or internal source. Each type of interrupt has a unique number called a vector number. Think of it as a label that tells the processor what kind of event just happened. Next, the processor uses this number to look up the address of the corresponding interrupt service routine in the interrupt vector table. It treats the vector number as an index, like flipping to a specific page in a book. Once it finds the address, the processor updates its program counter, which is like a bookmark that tells it where to continue running code. By loading the address of the interrupt service routine into the program counter, the processor jumps directly to that routine. The interrupt service routine then runs, doing tasks like reading data from sensors, clearing flags, or managing communication. When the routine finishes, the processor restores the previous state and resumes the main program exactly where it left off. Different microcontrollers implement the interrupt vector table in various ways. Some store direct jump instructions in the table, so the processor jumps straight to the routine. Others only store addresses, so the processor fetches the address first before jumping. In some systems, the external device provides an interrupt number, and the processor uses that number to find the right routine. This setup allows the system to respond quickly and efficiently to multiple events. The interrupt vector table must be at a known fixed location in memory so the processor can access it immediately when needed. Usually, the first entry in the table holds the initial stack pointer value, which helps start the system. The other entries point to routines for system reset, errors, and peripheral events. In microcontrollers like ARM Cortex-M, the vector table includes entries for system exceptions and peripheral interrupts. The hardware automatically uses this table to dispatch execution to the correct handler. Overall, the interrupt vector table acts as a quick-access directory that guides the processor to handle events promptly. It ensures that each interrupt gets the attention it needs without wasting time or causing confusion, keeping embedded systems running smoothly and reliably.